Hi, today I'm going to talk about the additional parts of Monte Carlo control. So last time, the biggest category that the Monte Carlo control falls under is the model free control, which basically is trying to figure out the optimal policy while we're not given information about the MDP, which is, in straight wordly, we could call it an unknown MDP. So when it comes to Monte Carlo policy iteration, as you can see in this slide, is basically alternating between the policy evaluation, which is basically computing the value or the action value for that specific policy. And then based on the updated values, greedily and steadily, incrementally improving the policy of interest. And in this case, we use the epsilon greedy policy, which epsilon is a hyperparameter that controls the rate of exploration and exploitation. So with the probability of epsilon, we enable random actions, which translates into exploration. And with the remaining 1 minus epsilon probability, we just exploit the up to the moment best greedy policy. So in this case, unlike the scenario that we only use the absolute greedy policy, by use of this epsilon, by enabling it, we now can explore states that we wouldn't have with the previous absolute greedy policy. But by definition, we want our policy, even though we enable some random action, at the end of the day, we want a policy which satisfies the global optimum. Even when you reach the end of the episode, if you're just continuing making some random action, then by definition, it cannot be considered as a global optimal policy. So in this case, we introduce a concept called the greedy in the limit with infinite exploration. So the formal details are here, but the main idea is that as the time step advances, we decrease the epsilon value, which again, to emphasize, epsilon you can think of as the rate of exploration. So as the time advances throughout the episode, we do decrease the rate of exploration. So in the end of the episode, the rate of the exploration will be very low, which means that the policy will converge to a global optimal policy itself. And by convention, they use epsilon value, like when we set the time step as k, 1 over k becomes our epsilon. So as k increases, 1 over k will decrease, which matches this idea of greedy in the limit with infinite exploration. Okay, so this theorem does guarantee that the Monte Carlo control would, on policy, Monte Carlo control would converge to the optimal. Then how about the temporal difference? So we emphasize that we can think of the Monte Carlo method and the temporal difference method in the opposite ends. The trade-off is that the temporal difference is basically the most naive one. It's basically making an actual interaction with the environment for one time step. And then after that one time step, until the end of the episode, of course, there are some scenarios, there's not even an end of the episode, but anyway, onwards from that one time step, we just estimated. We use an estimation for that instead of continuing the real interaction with the environment, which makes the Monte Carlo method. So the Monte Carlo method is basically interacting with the environment until the termination point. In this case, the bias will be very low because it's an actual result of a real interaction. Naturally, the bias is low, but the variance would be high. And that the reason for that is because when we're interacting with the environment, we choose the action. It could be a random action, greedy action, it doesn't matter. Anyway, we choose the action, but by this action, now there's again a random property there, which means that the environment randomly picks which state we will end up in by the action that we just made. So in the dynamic programming scenario, it was based on a probability distribution. For example, if I let's think of it as an example. Let's think as I'm trying to climb up Everest mountain, and my action could be I'm trying to anchor myself with some kind of tool. So I'm trying to hit 1 feet up from me on the snow. So that's the action that's controlled by me, which I make. But the consequence of that action really depends on the environment. That snow could be, in fact, too hard that my tool doesn't get in, which will give me a negative reward. But the environment could also somehow turn out to be that snow, that part where I'm trying to hit, is a very appropriate place to hit, which will ultimately lead me to a positive reward. So you can see that there's some randomness given by the environment as well, not only by me, the agent. So that randomness, since the Monte Carlo method is basically interacting with the environment until the termination point, those randomness is accumulated. There's so many randomness going on, which means that the variance will naturally be high, because in this episode, I made the same set of actions, but the result turned out to be this due to some randomness. But in the next episode, I make the exact same set of actions. But in that episode, the environment, there's some randomness there. So the result could be completely different. And that's why there's high variance problem for the Monte Carlo method, which tries everything. So to overcome that, there's the temporal difference concept was introduced, which is basically, instead of interacting from the beginning to the end, I just interact once, and then I rely on the estimation thereafter. But in that case, since we're relying on much less randomness, we're only relying on once in this case, one time step. However, the estimation thereafter, the estimation will not, there's no randomness in that estimation. It's just, there's only a bias problem because our estimation could really deviate from the true function. But anyway, there's no randomness there. It's just our bias problem, if there's a problem at all. So you can see that the Monte Carlo method and the temporal difference method are having a bias variance trade-off issue, as you can see in every other machine learning algorithm. Okay. So to dig into more of the advantage of the temporal difference learning, lower variance, and also we could do it online. So online learning is basically learning step by step. We make an action, the environment returns a reward, and then as the experience comes in, we update our policy and make another action based on our updated policy until we end up to some optimal policy that we desire. So with temporal difference, since we don't, okay, so for the Monte Carlo method, we have to interact until the termination point, which means that to get the mean. So basically, it happens like at some state, we follow our behavior policy, whatever, until we hit the termination point. And then we get we compute the mean, incremental mean up to that end of the termination, end of the episode. And then that means becomes the state, the value of the state or action value, whatever, for that where we just started, which means that we have to compute this, we have to throw the dice until we hit the termination point. That's a prerequisite. However, for this temporal difference learning, we don't need that. Since we're just estimating it, we could just, as you can think of it as like, as we're moving to the termination point, we are updating the value function instead of waiting until the end, which also this could be extended, have an extended advantage that we don't even need a complete episode. Monte Carlo method, we need a complete episode because we have to hit the termination point. But for temporal difference learning, we don't even need that because we're just estimating. Our t+1 to the end is just an estimation. So we could try it on incomplete sequences, which meets more of the everyday life, the interesting problems in reinforcement learning. Okay, so when it comes to the temporal difference learning in this model free control context, we could first go over two concepts of on policy learning and off policy learning, which is different. Is don't be confused with online and offline. Now it's on policy and off policy. And the off policy we'll discuss later, or not in this video, but here we will focus on the on policy learning concept, which on policy is a single policy governing the update policy and the behavioral policy. Okay, and the behavioral policy, in other words, is the action selection policy. So for the on policy, the policy that we're following and the policy that we're trying to learn is basically the same, which has which could have a disadvantage of getting stuck to the local minima because we're only reinforcing one policy more and more instead of enabling some randomness could make us explore some other policies that could lead to long-term benefits. But anyway, for a lot of, also even this approach, the on policy approach, could also lead to good policies. So the specific example of this on policy temporal difference learning is called SARSA, which is updating the action value instead of just the value. It's updating the action value, which is, in other words, a Q value. And we know this because, first of all, just as a reminder, when it comes to model-free control, model-free, we can't use just the value function because the value function, if we are only given the values of the states, then to determine the best or greedy action from that state, we will need some kind of probability distribution of assessing each actions, which action would lead to better results, which is basically the reward function. But reward function is only given in the model-based environment. Now we're talking about the model-free environment, so we can't use the value function, but we have to rely on the action value function. which is you can think of as an arrow from a state to another state. So it's there's no probability distribution here. So it's basically sampling from that randomness. We talked about randomness before, but now we're sampling. But so some environment actually just gives some returns a sample based on our action. And the reason for this algorithm being called SARSA is because as state S, we make an action A. Think the analogy that I made before, which is using a tool to anchor some point while we're trying to climb up Everest, and the environment will give us a sample back, which based on some kind of underlying distribution, it will give a reward experience associated with some reward. And then obviously that our action would lead to the next state. That's also randomness associated there, is determined by the environment. And then from that new state, our next state, one time step later state, based on our policy, current policy, I said it's on policy, so our behavior policy and our update policy is the same. So according to our current up-to-date best policy that we were updating up to this point, we could speculate that which action would we make in this new ST+1 new state. And that's where estimation property dives in. So to reiterate, at this time step, at this state, we make an action and the environment returns the new state, next state, and associated reward. And then at that new state, according to our current policy, we would make some other action, and that action would onwards lead to some kind of value, which this is basically be called as ultimate cumulative reward. So not only one time step advance, but up to the end, estimation of up to the end. So yeah, so for this SARSA, the specific policy that we are following is the epsilon greedy policy, which we went over. And okay, so in every time step, we again do the generalized policy iteration stuff, which is we evaluate the policy, which here is epsilon greedy policy, and then as that policy, we would update the Q values, and then based on the updated Q values, we again act epsilon greedily, which falls under the policy improvement part. Okay, so the pseudocode here is very simple, which again, here we can see that we choose some A from S based on our epsilon greedy policy, which is basically, and also is derived from the current Q function, action value function. And then based on the action that's chosen, we observe the reward and next state, which this part is randomly given by the environment. And then, as I said before, from that new state, we choose some, okay, so this choose A prime here is not that we're choosing, but it's basically what we would choose according to our current policy, which is epsilon greedy. And then based on that, we again calculate the Bellman error here, and then we move the current Q function for that state action pair a little, which when I say a little, it means that based on some alpha here, the step size, and we're incrementally moving here. So one thing to note is that this alpha could, in the Monte Carlo method, this alpha was 1 over n, which n was the count of how many times that state action pair was visited. So, and that's the the original way to calculate incremental mean. But now we're just using some alpha, which is a steps learning rate. So, which is a hyperparameter we could also control. So now we have the means to actually control the rate of how much we and this alpha, like 2 scenarios. If we're really obsessed to figuring out the global optimum, we could make this alpha learning rate very low. But if we want some fast convergence, then we could make this alpha high. And then we're repeating this. And one other thing to note here is that now, see, the next state S prime is being assigned to the variable S, big S, which means that we're actually going to make that action a prime here. So as you can see, this confirms that this is the on policy algorithm, because again, we're really reinforcing this epsilon greedy by choosing in both steps. And in the off policy, these two differ, but I'm not going to dig into it. Okay. So even this SARSA could converge to the optimal policy. And for that, again, there needs to be two, because it's using epsilon greedy again. Epsilon greedy can lead to convergence to the optimal policy. And since we talked about for this epsilon greedy policy to converge, we need to assume the Glee sequence, which we went over before, which is the gradient, the limit with infinite exploration. And also from this part is from the stochastic approximation theory, which is just saying that now we also care about the step sizes. So the step sizes should be like the first condition here is that connotes that it contains the meaning that the step size should be large enough so we can actually reach all the Q value could actually go far enough to hit the global optimal. And the second condition here means that, however, as time advances, as you can see in this summation sigma, as time advances, the rate of change of that Q value should be decreasing, which means that it should converge. But in practice, theoretically, these two should be satisfied to guarantee convergence. But in practice, in implementation, it's not really a thing to worry about. Okay, so again, SARSA, the SARSA that we went over, SARSA. So think of it as a temporal difference learning has a subcategory of SARSA. Okay, so as we saw in the temporal difference learning part before, temporal difference learning has a naive approach of only trying out one real interaction. And remember, this real interaction, which is in the function here. Okay, this is the most naive thing, as you can see here. There's only one reward, and this is what keeps guarantees convergence to the optimal, because the second term here, which is this, is the discount rate, and this is the Q value onwards from the next state. This is an estimation. This could be completely wrong. Even in the beginning, In the beginning, we just randomly initiate this Q values for all states to some random value, which all could be 0 or whatever. But this R comes from the real interaction, which keeps this algorithm to be grounded to the truth of this MDP. However, if we are only relying on one, this could have, again, this could lead to a higher bias issue, because the second term here is estimation, and we only have a realness of one term, higher bias, lower variance. But so now we introduce the n-step concept. In another scenario, we could use 2 real interactions and the rest rely on estimation. And for the 3-step, we could rely on 3 real interactions and the rest rely on estimation. So this could go up to n, and n, which n is a hyperparameter and could be infinite as well. And if this n is infinite, this is just for notation, but if n hits the termination time step, it's exactly the same as the Monte Carlo, so SARSA, this is again the trade-off between the temporal difference and Monte Carlo method again. SARSA is just a subcategory of the temporal difference learning, an on-policy subcategory of temporal difference. Okay? And again, when it comes to n-step SARSA, this n is a hyperparameter that could lead to very different outcomes depending on which value gets plugged into this n. So, and figuring out this n is very difficult, and so many randomness, it has so many randomness involved, so it's not really a good idea to try to figure out the n. Rather than that, as we went over before, we introduce a lambda concept involved with n-step lambda concept, which means that this lambda, which is a hyperparameter, is basically controlling the bias and variance between the SARSA and MC. So, okay, in other words, it's just trying to get the specific implementation. There's 2, which is forward view SARSA and backward view SARSA. And okay, so forward view, they're basically doing the exact same thing, but they have some differences. To just first go over the forward view SARSA is trying to get the geometric average mean of these of the reward functions across different n steps. And this specifically, the weight is 1 minus lambda times lambda to the power of n minus 1. And this first term of the product, which is 1 minus lambda, is just a normalization factor, because we want to add, when we add this up, we want to guarantee that it equals to 1, because we're trying to get some kind of a mean, right? And our interest relies on the second term of the product, which is lambda to the power of n minus 1. So as you can see here, when let's say that lambda is 1, which means that here lambda, the first one step SARSA will become 0, right? Onwards, up, and only up to the n step will all become 0, but only the last step will have weight now if lambda was given as 1, which is exactly the same as Monte Carlo method. But when lambda is 0, then in this case the end one will no longer have any power. And also, only when lambda is 0, only the one step SARSA here the most naive one will have a weight. So we can see that this lambda is as we tweak it, we're oscillating somewhere in between the SARSA and the Monte Carlo. Okay. But the problem of this forward view SARSA is that we have to wait until the end of the episode. So it's not an online learning, it's an offline learning algorithm. You remember that online is basically step by step. We are updating our action value function step by step, while offline can't do that. So since with the forward view we have to wait until the end of the episode, this has a disadvantage that we cannot do the online learning. So, and I also talked about that there's a exact same another implementation detail of this SARSA, lambda SARSA, which is backward view instead of forward view, because forward view suffered that kind of offline this advantage that it can't do online learning. They introduced an algorithm called backward SARSA lambda. So the idea we went over before in another video, but it's basically that, okay, to first emphasize, they're doing the same thing. Even though it's not straightforward that they're doing the same thing, they're using the same lambda here, despite the formulas that used between them are completely different, okay? But they're doing the exact same thing. And the backward view, how is this backward view SARSA tweaking its lambda to do the same thing, okay? So it's using a concept called the eligibility trace, which enables an online algorithm. So you can think of it, instead of trying to estimate and see, let's say that I'm at some state at time step t. In the forward view, I kind of mix up t+1 onwards, t+2 onwards, t+3. So it's about forward, as the name suggests. But the backward view, I keep track of which state to blame, to give credit for my current update. Which update here in information theory is basically how much the environment showed me a surprise, because my estimation was this, but the environment gave me this return. So the difference between my estimation and the actual return from the environment is a surprise. So which state which I passed before should be attributed, like which should be to be blamed for my current update. So, and basically eligibility trace has two heuristics, which is the recency heuristic and the frequency heuristic. So you can think of as, let's say that we has passed some kind of states, and we could naturally think the states, the action states, action pairs that happen the most should be kind of more responsible for our update compared to the state action pairs that didn't even really happen that much. So that's the frequency heuristic. But there's also a recency heuristic, which we could speculate that the most recent event is responsible for the update that happened today. So we are kind of mixing up these two heuristics to figure out how much credit I should assign to each state that I passed through. We don't care about the state that we do update for the we don't really care about the states that we did not pass through this episode. Only the state we just did. Okay. So in this case, formally this, as you can see here, this variable e is basically showing the two heuristics that I talked about just right now. So the second term is this is the indicator function. So this gets, so basically this variable of E, eligibility trace, is getting added by 1 if we actually select that state action pair. So which, as this indicator function suggests, if we really visit that state action pair, we add 1 to the E variable. And the first term here, this is a discount of the reward parameter, and this is a lambda parameter, which also has some kind of discount value, as we also have seen in the forward view SARSA lambda, which seems they're the same lambda, right? So this lambda is kind of assigning some weight to each state action, like, yeah, you can think of it as that kind of factor. And then we're discounting all of the eligibility trace. So in implementation, for every state action value pair, we have, so we can think of as we construct a matrix. Think of as row as all the states, and the column as all the actions. And then the data cell corresponding to that state action pair will have the eligibility trace value. And then as one time step advances, we are discounting it. Because like, for example, let's say that we got a real surprising event at time step when t was equal to 30. Okay, no, t was when t was equal to 100. It is more plausible and reasonable to think as that 100 should be more credited to the states that were happened more recent, instead of some kind of time state that happened when in the beginning, when everything was random, right? So that's why as time goes by, we want to decrease the rate of the eligibility trace, which eligibility trace variable here is what is the factor that determines how much our Q value will be updated, as you can see in the last formula here, right? But also, as I said, this lambda is a hyperparameter which is tweakable, so you can do anything. It's between 0 and 1. And if you want to, if you really think that an event that happened in the initial time step can be responsible for the event that surprising event that happened in time step like 1000, if you really think that's capable, then you can just set lambda as 1. You're just equally treating all the state action values pairs that happen in your trajectory equally. But if you think that's unreasonable, then you can decrease it, and then as it will be decreased, it will, because lambda is between 0 and 1. If some value between 0 and 1, as you multiply it again and again, it will converge to 0, right? So that means that as time advances, the older state action value pair occurrences will have less and lesser weight. So that's the intuition. And again, yeah, we went over the SARSA, the naive, the one-step SARSA algorithm pseudocode before, and this is the pseudocode for the SARSA lambda algorithm, which has the structure is very similar, but it has very different details. So okay, so again, we initialize, as I said before, just in a naive implementation, we are just constructing a matrix of state action value pairs with the data cell of the value of the eligibility trace value. Okay, so initially we obviously have to initialize it as all 0 because we have no idea what's going on. And then we we enter into one for loop, which is taking action A, some action A based on our epsilon greedy policy, and then the environment returns reward, associated reward with that action, and the next state based on its own MDP, which we don't know because we're in a model-free algorithm, okay? And then based on that next state, we would speculate which action, the next state action, we would take based on our up-to-date current most state-of-the-art policy. Like don't confuse that when I say state-of-the-art, because epsilon greedy policy is the policy that we are using, but we are basically improving that epsilon greedy policy more and more to match the MDP, which in the end, our epsilon greedy policy would be revised so much better so that it would be the optimal policy. That's what we're aiming for, okay? And then we calculate the Bellman error, simple difference, TD error, in other words. And then here, this part, in the concept here, we just express, in the formula here, we just expressed it into one equation, but in the pseudocode, we're doing it separately. This part, updating, incrementing the eligibility trace for, and this big capital SA means that a specific real actual state action pair. Since we just chose it, we are incrementing, we are keeping track that we chose it by adding 1 to the epsilon, the eligibility trace for that specific state action pair in the data cell. Like in the matrix, we're updating just to one data cell that corresponds. And this in the equation corresponds to this indicator variable, indicator function. And then the first term here, the discounting part, discounting by the discount reward factor, and the lambda is happening in the pseudocode in this inner for loop. So, but here note that unlike the just one line above, we are only dealing with one specific state action pair. But unlike that, now we're updating for all of the state action pairs in the matrix. In the naive implementation, I said that we're using a matrix. We're updating for all of the data cells that are in that matrix. But even in this case, so it's highly possible that the data matrix is very sparse, because if we didn't really go over many episodes, a lot of the data cells, if we assume a very high dimensional state action space, it would be very sparse if we didn't go a lot of episodes, because the trajectories would not likely cover all of the space. It would have some kind of pattern to reach to the terminal state. So except for that non-zero data cells, everything even will remain as 0 because we didn't really hit that state actions, because what we're just doing is multiplying that 0 by some discount factors, which discount factor times 0 is still 0, right? So yes, that's the intuition. But again, so because in this case, but also it is very true that if the state action pair is very high dimensional, which is also a problem of this naive implementation itself, because we're traversing all those state action pairs. So it could be very computationally burdensome, very heavy, which later leads to the value function approximation technique, but that's out of the context here. Okay, so okay, just the thing to remember is that don't be confused with this equation. This equation, the second term, in implementation in the pseudocode is only dealing with one state action pair, while the first term here, the discounting, is dealing with all data cells, all of the state action pairs available in the MDP. And then as you can see, we're just updating the S variable into the next state which the environment gave, and the action also, right? The action which is based on our speculation, we are realizing it in the reality, right? Which means that, again, it's kind of a loop. We are reinforcing our E-greedy, which does not necessarily lead to local minima, but we are giving, there's no differentiation between the update policy and the behavior policy. We're just using the same policy for both, which is by definition the on policy.